Hello and welcome to part 6 in our series. This time we're going to start looking at can we optimise the code, the C# code we're generating. Because at present, for example, if we look at our sample, so if we look at hello world for example, we've got these duplications, which means instead of just creating a single command, we're creating like 6 commands to add one, add one, add one, instead of where we could just do add 6. So before I start though, I've made a couple of little changes since the last episode. I split out all the instruction classes into their own files to make things a bit tidier, and I've also pulled out all the hard-coded C# code into a set of template files. So we've got the project file, we've got the header which appears at the top of our generated code, and we've got the footer which appears at the bottom. And with the header I've also got this tag which I'll replace when we're using this template with the namespace we're going to use. And if we look at the properties of our file, you can see I've set them as embedded resources. So within the program, I read out the embedded resource in the assembly, and then I replace the markup tag we need, and I return it as a string, and so on. So the idea is, as we've built up our object model or our graph of the existing symbols, we can then just optimize that in here. So the idea is, we start off with our root block as before, and then we pass that to an optimize method, and it's going to return a optimized root block. So I've had a few attempts at writing this when I was preparing for this episode, and it's not all that straightforward, so we shall see how we get on today. So what the idea is we want to keep everything immutable. And so the idea is we're going to have to create a new block at this point. And the mistake I made when I was preparing for this is I forgot to set the parent, so we need to do that as well. And so we actually need to pass in a parent. So the idea here would be that we create a new block, add in all our existing instructions, and then return the block. And then that would be as if we haven't actually optimized it, but the meaning of the code hasn't changed. So it's going to be in our root block. So if that compiled, then that would be sort of our optimized routine, not actually doing anything at all. So first of all, we need to make that compile because we don't actually expose the list of instructions within a block. So let's do that. And because we want to keep things immutable, we shall return a read-only collection of instructions. Okay, so now we actually want to start combining them together. And the way I think we need to do this is we need to keep track of the previous instruction. And if it's one we can combine with the current instruction, we do so, otherwise we just write it out. Which means each time around the loop, we need to look at the type of each instruction. So we can just do a sort of a traditional switch statement for that. So let's do, well, okay, we're actually going to do loops first, because although they're the most complicated, they actually also turn out to be the simplest in this case. So when it's a block, so we've hit a loop command, then what we need to do is optimize our loop and it's now going to have a new parent, which is the block we're now in. Okay, and then there's a couple of commands we can't optimise, and these are write to console and read from console. So for these two commands, we're just going to simply add them to our new block. Okay, so now we get to the more interesting ones, which are the 4, where we can actually optimise them. So the first one is move left, so when we're moving our data pointer to the left. So if it's the same as the previous command, we can add it to the previous command. If it isn't the same as the previous command, we need to create a new command. So we need to keep track of what the previous command is. I'll just call it previous. And we only need to track the previous command if it's something we can actually optimise. So in this case, we don't actually care anymore because we can't optimise that command, so we don't need to do anything with it. However, if we did have a command, we'd actually have to have printed it out. Actually have to include it. This will probably make a bit more sense in a second. So then now we've got to work out how we're going to represent these combined commands. Because at the moment we've got one command for moving left and one command for moving right. So what we really want to do is actually have a quantity in here which will move how far we're going to move to the left, how far we're going to move to the right. But it turns out moving left and moving right is the same thing. One's just a positive value, one's just a negative value. So what we can do is actually create a new class. Oops. In fact, let's just copy this one. And we can just call our new class move. And the difference is in its constructor we can pass in the quantity we're going to move. And the property, and so when we're emitting it, if the quantity is greater than 0, we say it's going to be plus equal that quantity. Else, if the quantity is less than 0, we do minus equal the positive version of that quantity. And if it is 0, of course, we just don't need to emit any C# at all. So that handles that, I think. So we just move that to its own class. So now we can say in our code, if our previous instruction was a move command, our previous instruction is a move command, we can just change our previous instruction to be a new move command, which is its current quantity less 1, because we want to move it one more place to the left. Else, if the previous instruction is something else, then we now add what we used to have, and we start a new command with just -1. So so I think it's going to turn out the only other type of object it can be is just like an increment or decrement of a value, because we can't combine those with moving left and right. So let's do moving right, should be a simple one. So again, we can combine it with a previous move, in which case we're going to add 1, and otherwise we've got to create a new command of just 1. I think that makes sense. So now we want to do something similar with our increase and decrease. So we want to create a new class that combines them both. We just call this one increase cell. And exactly the same as before, we'll add a quantity. And we'll add that as a property, as a read-only property. And as before, if the quantity is greater than 0, do plus equal quantity. Oops, it was a bit dangerous when you miss those off. Or even if you put the wrong one. Right. Now, so if quantity is less than 0, minus equal and minus in there. Okay, that looks good. So now, hopefully, we can just copy our 2 cases from here. So moving left is the same as what is decrease. Strange how these variables aren't used, but I guess that's because these classes didn't actually hold any information before. It was just a type of class is the only thing we care about. And finally, we can do our increase, which is +1. Okay. So the idea is we call optimize in order to rewrite our block, and we do this by keeping track of the previous instruction in that block. If it's one that can be combined with the current instruction, we do combine them. Otherwise, we print out what was the previous instruction, and we've got a new instruction to work with next time. These commands, however, can never be optimized, in which case we always just print out what the previous command was, and then add what the previous command was, and also add what our new command was. In the case of loops, however, we can then optimize that loop in turn, so we sort of recurse down, calling that. But the important thing is to make sure we set the new parent for each block as we go. Okay. Okay, that's that. And yep, it's got the right time. Okay, so that hasn't worked at all. So it's obviously running our new code, but it hasn't combined anything together. So this is in the increase. The previous was an increase. Right, worth just debugging actually, because the file starts off with some pluses, so it should be quite straightforward to follow it through in the debugger. So to begin with, we'd expect our previous to be null. Oh, that's not right, is it? Ah, we don't need. I think we don't need this. So if the previous command is a move command, we can add to it. So the next case is there is no previous command, in which case we still need to create that. Yes, so we don't need. I just want the else. Because there's three cases. If there's no previous command, but then we can't add it to the block, but we do want to create a new previous command. That's the case we're missing. So now when we step through, yeah, that's better. So this time through, we now have a previous command, so we can now add our quantity to it. So that should be 2. Yeah, so let's run that through now. It's half worked. It's printed out both the old command and the new combined one, so it's still not quite right. Ah, it's because we got this down here. Our example code from before. Which means, actually, yes, if we finish with one of these commands, we do actually need to add that as well. So at the end of the loop, if we've actually got something left over, we need to make sure we add that. Otherwise, we're always going to lose the final command in each block, which wouldn't be good. Okay, we've now got a new problem. Ah, because I've put that on the wrong side. The braces. Yes, that's looking a lot better. So you can see it's combined those 8 adds into one, and got some with the data pointers combined. Yes, down here, data pointer plus equals 2, and a minus 1. So I guess the proof would be if we run our compiled program. So it's got the current time, that's good. And yes, that's still working. Go back to here. So at first glance, we would imagine it would be possible to say optimise this code, because these values never change, because there's up to the first, well, really none of these values change, because we've got no input, so we've got no console.read line anywhere. So in theory, you'd imagine you could actually you could actually optimise this down to be just h the LLO, etc., and just write out hello world. However, I think the only way you can ever do that is by actually evaluating the whole program, and that's not actually technically possible. So I think the best we can do would be able to work out the values of things up to the first while statement, where it's all just sequential. Because the problem is, as soon as you get up to a while statement, you can never prove that while statement is ever going to terminate, so, which means you can never work out what the value is going to be set to. Which means the best you can do is prove that our first cell contains the number 8, which is pretty much what we have anyway. So that I think, unless anyone knows otherwise, that's about as optimal as we can get it. In terms of our code, however, this and this do look very similar. I wonder if we can pull that out into a method. That looks like it's offset. And that one comes +1. That looks better, doesn't it? And we can combine those two in the same way. So that's before we're passing its offset. That looks a lot nicer, doesn't it? Don't think it's worth doing anything with these. They're all, yeah, I mean, it's a bit not horrible in that it has this side effect of resetting what was the previous value, so it's not great. Better just make sure our code still runs. And that's still working. Right, well, this video has been a lot longer than I was intending for anyway, but hopefully you can find that interesting, and it seems to be working as we would hope. So see you next time.